Imagine a car that travels along a straight road at a constant speed of 20 meters per second. The velocity versus clock reading graph looks like this. We know that every second the car travels 20 meters. Previously, you have seen that displacement of the car can be interpreted as the rectangular area under a velocity graph. The displacement of the car is represented by a rectangle that is 1 second wide and 20 meters per second high. Multiplying 20 meters per second by 1 second, we can interpret this as the area of the rectangle. This area is 20 meters and is the distance that the car travels every 1 second of elapsed time. For a 4-second time interval, say between 2 seconds and 6 seconds, we can view the displacement of the car in that time interval as the accumulation of 4 successive 20-meter area rectangles totaling a displacement of 80 meters. This means that the position of the car at 6 seconds minus the position of the car at 2 seconds is 80 meters. And another way of saying this is that wherever the car was at 2 seconds, information we do not have, the car is now 80 meters further down the road at a clock reading of 6 seconds. Let's consider a more challenging problem. A toy pullback car starts from 0 velocity, speeds up for 4 seconds, then slows down and comes to a stop at 8 seconds. In this example, let's suppose we know the shape of the velocity versus clock reading graph to be described by negative 1/4 t squared plus 2t. How far does the car travel between 2 seconds and 6 seconds? This is a harder question because the speed of the car during this time interval is not constant. To estimate the displacement of the car, we could draw 4 3 meters per second high, 1 second wide rectangles for a total displacement of 12 meters. But this would be too low of an estimate because the car goes faster than 3 meters per second. Or we could draw 4 meters per second high, 1 second wide rectangles for a total displacement of 16 meters. But this would be too high of an estimate because the car only travels 4 meters per second for 1 instant and the rest of the time is traveling slower than that. Or we could try and compromise and draw 4 3.75 meters per second high rectangles for a total displacement of 15 meters. But all of these methods are just approximations. Is there a way to exactly calculate the displacement of the car? That is the goal of this video. In exploring this, we are going to talk about the fundamental theorem of calculus. We only know how to handle situations with constant speed, so let's approximate the velocity versus clock reading graph as a set of straight-line constant speed segments, each segment 1 second long and taking the value of the speed of the car at the beginning of that time interval. Then we can draw 1 second wide rectangles underneath whose heights are given by the speed of the car at the beginning of that interval. Having broken the curve into 4 rectangles, we can approximate how far the car traveled in each second by assuming it traveled at a constant speed during that interval and multiplying the height of the rectangle by the width to find 4 displacements. Summing those 4 displacements together, we can estimate the total displacement of the car in a 4-second time interval. How accurate is this estimate? There is a way to calculate the exact displacement which we are working towards. With 4 rectangles, we are 1.1% under the actual displacement of the car. How can we improve our approximation? The solution is to make the time steps we use to approximate the velocity versus time curve smaller and smaller. We can break the segment into 8 rectangles using time steps half as big as before, then 16 rectangles, 32 rectangles, 64 rectangles, and finally 128 rectangles until we have an estimate of the displacement that is about 1/1000th of 1% below the actual value. This is quite remarkable. It suggests that with small enough time steps we can get as close as we like to estimating the true displacement of the car between 2 seconds and 6 seconds from the velocity graph by approximating the velocity curve with many small straight line segments. We want to be able to calculate the exact displacement, knowing the velocity versus time equation, and to do this we need to connect what we just explored to calculus. To make this connection, I will formalize the notation and generalize the discussion. I will use delta t equals tn minus t0 to represent the entire time interval for which we are trying to estimate the displacement of the car. Hopefully the rectangles demonstration we just did has convinced you that the total displacement of the car in this time interval is the area under the velocity versus time curve between two clock readings we just identified. I will use delta x to refer to this total displacement between the initial and final clock reading. dt represents the width of one rectangle under the curve, where dt is defined as delta t divided by n, where n represents the total number of rectangles that we're going to use to approximate the area under the curve. I will use dx to refer to the area of this rectangle, and it represents the approximate displacement of the car in the time interval dt. It is the height of the rectangle multiplied by the width. It should make sense that the smaller the width dt is, the more accurately dx approximates the actual displacement in that small time interval. The total displacement is therefore the sum of all these small dx displacements, which is the sum of the speed of the car at each point times the time interval dt. In the limit that we make n sufficiently large, this sum of many tiny rectangles is written as an integral over time between the starting time and the ending time. Is there a mathematical way to solve for the position as a function of time if we know the mathematical expression for the velocity as a function of time? In other words, we want to find x of t, which is the solution to the integral of v of t dt. The starting position is just a number which we could make 0 if we wanted to. To figure this out, let's consider some intermediate step in the process of finding the position from the velocity graph. At some clock reading t, we can say that the car has traveled a certain distance x of t up to that point. This is represented by the shaded area from 0 up to the point shown on the graph. In the next time interval, dt, the car undergoes a small displacement, dx is equal to v of t dt as shown. Thus, the total accumulated distance traveled, including the extra time interval dt, is x of t plus dt, which equals the original distance x of t plus the additional v of t dt. We can arrange this expression in the following way. If we consider the limit that dt goes to 0, we get the key result, which is known as the fundamental theorem of calculus. If we know v of t, the answer to the question, what is the integral of v of t dt, is the position graph x of t, and more importantly, x of t is a function whose derivative is v of t. In other words, the mathematical solution to the integral is the antiderivative of v of t. Pause and ponder for a moment. If the velocity graph given by -1/4 t squared plus 2t, what function of time would you construct for x of t? You can figure it out by thinking about what function of time, when you take the derivative of it, will give you -1/4 t squared plus 2t. The answer is -1/12 t cubed plus t squared. To check that this is correct, just take the derivative of this function with respect to time and make sure you get the velocity function. We can now return to the question of what is the displacement of this pullback car between a clock reading of 2 seconds and 6 seconds. It is simply the area under the curve between 2 and 6 seconds, which is calculated by substituting the time into this position equation we just derived, giving us a displacement of 14 2/3 meters. In conclusion, pause for a moment and understand what we have been able to accomplish with a seemingly naive and simple idea of breaking the area under a velocity versus time curve into small rectangles. Not only have we been able to calculate the displacement of the car, we have been able to provide an intuitive proof of the fundamental theorem of calculus, namely that the answer to the integral of v of t dt is the antiderivative of v of t, which is the position versus clock reading graph x of t.